In this video, I'd like to do a couple of examples where we can apply Gauss's law qualitatively to be able to think about what's going on in some surfaces. Okay, so in the first example, let's say that we have a uniform electric field. So I'm just going to have an electric field that's pointing to the right with some magnitude everywhere. Okay, and for this case, I'm going to draw a Gaussian surface in the shape of a cylinder. Okay, and remember, the Gaussian surface is not actually there, it's just a thing that I've drawn. It's a mathematical structure with no physical presence at all. Okay, so this surface has three parts. It's got a left-hand part with an area vector that points to the left. Behind, there's an area vector that points to the right. Okay, so same magnitude, opposite direction. And then for the curved part, I'm going to have dA vectors that kind of point outward like this. Okay, so you just have to draw a couple of representative ones for that part. Okay, so what I want to do then is use Gauss's law. So Gauss's law tells me that the total flux is equal to the charge enclosed over epsilon naught. And notice that the surface I drew has no charge enclosed. There isn't any charge there. So the total flux needs to be zero. Well, let's see how that works. Okay, so if I consider the flux along the left-hand side, so the electric field going into that surface, then it's equal to E dot A, where A is the area of the left-hand side. And notice that E is to the right and A is to the left. Okay, so this is then going to give me a 180-degree angle between them, which has a cosine of -1. So that will be negative E times A, left. All right, so there's a negative flux on that side. I have the area vector pointing outward, the electric field points inward, so a negative flux. Okay, looking at the right-hand side, I'm going to still have E dot A, but this time it's the area vector for the right-hand side. Here, the electric field points to the right, the area vector points exactly to the right, and so here we'll get positive E times A of the right-hand side. Finally, we have to consider the curved side. Well, here, the electric field is to the right, but the area vector, if we look at the top one, points directly upward. All the other ones will point outward radially. So you should take a minute to convince yourself that E times A, well, times dA in this case, is 0 because E is perpendicular to dA. Okay, so that's true, and the total flux is equal to the flux of the left plus the flux of the curved side plus the flux on the right. And the flux to the curved side was 0, and the flux to the left and right are equal and opposite, EA and negative EA, so those all add up to 0. Okay, so we can see in this case that Gauss's law is true. Okay. Notice that the fluxes are scalars, so we can just add them up. Fluxes do not have a direction associated with them. We don't have to worry about a component of flux. We just calculate the flux and it's a number, and then we can do whatever we want with it. We don't have to worry about anything. Okay, so that's one example. Let's do another example. Okay, so in this case, let's consider one where we actually have a charge present. So I'll put a charge here, and oops, and then I'll draw some electric field vectors like this. Electric field lines, I mean to say. Okay, that's good. And again, we can draw any Gaussian surface that we want. So I'm going to draw a pretty weird one here. I'm going to take a shape that's a circle on this side, and then the side follows along these electric field lines, and then it's going to be kind of like this. Okay, so sort of a truncated cone sort of shape. Okay, and that's my Gaussian surface. Again, not actually there, just a thing that I've drawn. All right, so if I draw area vectors for this, well, here I have my area vector points inward, and out here it points outwards. And then over here it's going to point in some various directions, but always perpendicular to the surface. Okay, a little tricky to draw in perspective, but hopefully you get the idea. Okay, so again, the total flux is going to be the flux from the close side plus the flux from the curved side plus the flux through the far side. Okay. And notice that I picked the shape that I did because for the curved side, I can immediately see that E is perpendicular to A, and so this equals 0. Okay. So what this tells me is that the total flux is just the flux through the other two sides. Okay, and notice again, there's no charge enclosed, which means that the total flux is equal to 0. Okay, so then 0 is equal to the flux through the close side plus the flux through the far side. All right, so we can conclude then that the flux through this side over here is the same size but opposite sign as the flux through this side. Okay, so how does that work? How is it possible that those are the same? Well, what we notice is that the close side has a small area but a large electric field. And on the far side, it's got a large area but a small electric field. Okay, so doing this example, we can see that those two things happen to cancel out exactly. And in fact, you could use this to argue that the electric field needs to decrease with a 1 over r squared relationship. We'll do that in a slightly different way, but this is a starting point that you could use to show that. Okay. And notice that we can pick any shape we want for the Gaussian surface, but the trick that I did here, where I chose a surface where at least part of the surface gave me E times A is 0, is going to be a trick that we'll keep using. So that will make the calculations easier as we go, and we will keep doing that as we go.